So in this video, we're going to go over some hints for problems 110 through 113. In problem 110 and 111, you have a baseball which is thrown, and in most of the situations, the baseball has some initial velocity in both the x and the y directions. While the baseball is in the air, the only force acting on the baseball is the force of gravity. This means KE1 plus GE1 is equal to KE2 plus GE2 because the work done by forces other than gravity is 0. In addition to this, you also need to know how to break the initial velocity down into components. So in some situations, the velocity is already only in the x direction or only in the y direction. But if you have your initial velocity vector going off at an angle of theta from the horizontal, then you find the x component by taking the magnitude of the velocity vector and multiplying it by cosine theta, and the y component is equal to the magnitude of the velocity vector times sine theta. And if the only force that you have is the force of gravity, then the x component of the velocity does not change while the ball is in the air. If you are looking at the initial kinetic energy, remember that kinetic energy is equal to 1/2 the mass times the velocity squared. This velocity is the magnitude of the velocity vector, so you could also write this as 1/2 times the mass times the magnitude of the velocity vector squared. That's the length of this vector. And we have a right triangle here. You could write the length of this vector as Vx squared plus Vy squared all to the 1/2. So in 2 dimensions, you can write the kinetic energy as 1/2 the mass times, you would have this for the magnitude of the velocity vector. Let me put this up here. That would be the square root of Vx squared plus Vy squared, but you're squaring this, so that becomes Vx squared plus Vy squared. So it's the square root, but then you square it, so that gives you this, which is still going to be positive, so that's good. So that's how we find the kinetic energy. And we can use that along with the work-energy relationship when the work is equal to 0 to answer 110 and 111, and you need to remember how to break the velocity, the initial velocity, down into components also. You may need to also use some of the kinematics formulas that we had back in Model 1 for Part B of 110. Depending on how you look at it, you really don't need to, but you might want to just to check your work. For problem 111, all you need is the work-energy relationship. The work done by forces other than gravity is still 0. And remember that this is the speed. So you're told for 111, the baseballs are all thrown at the same speed, so no matter what the angle is, this is the same for all 6 situations. You want to rank the baseballs on the basis of the speed the instant before they hit the ground. So let's do this. For problem 111, they all start with the same kinetic energy. So KE1, because the mass is the same and the initial speed is the same, this is the same for all 6 situations, plus GE1, which is m times g times h. In this problem, they give you capital H for the height, which is different for the 6 different situations, is equal to KE2. This is 1/2 the mass times the speed squared. So let's write this as Vx final squared plus Vy final squared, and it's this in parentheses, which is the final speed. So it's that quantity which you're looking for, plus GE2. But you can just say ground level is 0, and you can use this for 111. The situations in 112 and 113 are similar. In both cases, you have a block on an incline, and you are told in 112 and in 113 that the force of friction is negligible. So we're going to ignore friction. You have your mass on the incline. You have a force of gravity acting downwards. But when we look at work done by forces, it's not there, work done by forces other than gravity, that does not include the force of gravity. And we have this normal force. But when the block is sliding on the incline, the displacement is perpendicular to the normal force. And if we're ignoring friction, the normal force is the only force other than the force of gravity that we have. The normal force does not do any work when the object is sliding on the incline. So work done by forces other than gravity in this situation is 0. So once again, we have KE1 plus GE1 plus KE1 plus GE1 is equal to KE2 plus GE2. And in all the situations for 112 and 113, the crates are released from rest. If they are released from rest, then the initial kinetic energy is equal to 0. And then if we set the 0 point of gravitational potential energy to be at the bottom of the incline, we can say GE2 is equal to 0. So now we have GE1 is equal to KE2. And you may want to also use MGH, let's call this MGH1 for GE1. And kinetic energy is equal to 1/2 the mass times, let's call this V2, and it's squared. So this is the final speed, and it's squared at the bottom. So you can use some combination of what we have here for 112 and 113. For 113, however, unlike in problem 112, where they give you this height, they call it capital H in 112, but let's just use lowercase h, which is what we have here. Instead of giving you that height, in problem 113, they give you this distance here. That's capital D, and they give you the angle. If you know this distance, you should be able to calculate this height using a little bit of trigonometry. So you'll have to do that for problem 113. In problem 112, the height is the same for all, so you can just call the height 1 for each of the situations. In problem 113, the angle is changing, but this distance D is the same for all situations, so if you just want to call this D1, that will not affect the ranking.